Welcome back. In the last class, we discussed a lot about scalar couplings, multiplicity patterns, everything we understood. We also try to analyze some of the spectra artificially by synthesizing using a familiarity approach. It is not a realistic spectrum. Giving a hypothetical molecule with hypothetical values for the coupling, we wanted to simulate the spectrum, synthesize and see how the spectrum comes for a given molecule. The classic example we took was CH2D2, where carbon 13, proton and deuterium, all the three different nuclei are there. One is natural abundance of 1%, other two are labeled. Deuterium is the 100%, and at the same time, one is spin 1 nuclei, other is spin half nuclei. We could get this multiplicity pattern very easily. So, and we also understood quite a bit about varieties of multiplicity pattern and what is the nomenclature adopted in naming the multiplicity that we see when one spin is coupled to varieties of other spins, both chemically equivalent or non-equivalent. So we understood quartet, doublet, triplet, septet, pentet, and multiplicity is like triplet of a quartet, multiplicity like triplet of triplet, triplet of quartet, all those things we understood. We are using that idea now to analyze some of the simple molecules, simple spectra of proton and other nuclei. So today we will come back and start with what is called analysis of the spectrum. I take the simple molecule 1-chlorobutane. It is a very simple molecule whose structure is given. It is a realistic spectrum. It is not synthesized. So now looking at the molecule, you can say there are 4 different groups of spectrum. Obviously you must get 4 different types of coupling, 4 groups of proton peaks. Of course this is a reference TMS. Now basically the knowledge tells me CA3 groups generally comes in the high field region. Around 0 to 0.5 to 1 or 1.5 ppm, CA3 group will come. So this must be, my first guess is CA3. Okay. If this is CA3, then it is a triplet. Why it is a triplet? It is because you can see that this is coupled to CH2. This is coupled to CH2. Because this is coupled to CH2, that CA3 has to be a triplet. That's correct. Now, what is happening after that? Another easiest thing to understand is this CH2, which is attached to chlorine. Because chlorine is an electronegative atom, it withdraws the electron from the CH2 and comes to the downfield. So this must be a CH2 protons attached to chlorine. And why it is a triplet again? Because this is adjacent group is again CH2 and it is a triplet. Very easily we understood. Now remaining 2 protons, remaining 2 groups, how do you understand that? Very easily you can understand. Remember here one important thing, you should go by the multiplicity pattern here. See, if you go by the multiplicity pattern here, now consider proton B. If I take proton B, the proton B complexity is much more than proton C. The reason is this proton B is coupled to CH3 and CH2 both. So because of CH3 it is going to be a quartet, and then each line of the quartet is going to be a triplet because of CH2. This is a more complex pattern. Whereas on the other hand, proton C, it is coupled to 2 CH2s. It is going to be triplet of triplets. That's what we understood earlier in the multiplicity pattern. So the one which is more complex should be proton B. See, this is more complex. I would say this is proton B and this is proton C. This is how, based on the chemical shift, based on the multiplicity pattern, because of the scalar coupling, you can make the analysis of the spectrum, given spectrum. Now we will look at the another molecule, 2-methylpropanol. This is very easy to analyze. Very simple molecule. Looking at the molecular structure given here, one is CHO, already group is there, CHO. This, because of the CO, will come to downfield. So this must be the CHO proton. And of course this is going to be a triplet. Why it is a triplet? If you look at this, why it is a triplet? Very easily from the spectrum, you will, from the structure, you know, this CH has a long range coupling with this CH proton. So because of that long range coupling, this is going to be a doublet because of coupling with this proton. This proton splits this into a doublet. Now let us see what will happen to these 2 CH3s. These 2 CH3s are here, they are equivalent. They are not equivalent. but this will couple to this proton and will become a doublet, and that has to be well resolved here. In principle, it is going to be doublet of doublets. Doesn't matter, resolution is poor. Look at the CH proton here. The CH proton, these two methyl groups are chemically inequivalent, and each of them will split this into a quartet. And each line of the quartet is further split into a quartet by CH3 group. But also it has a long range coupling with CH. So it will become quartet of a doublet. And it's a very complex pattern. You can look at it here. This is a very complex proton spectrum. And of course you can analyze, it's not so difficult. One can start looking at it and analyze very easily. Now you look at it, this is another easiest way to understand. Very simple spectrum. There are 6 groups of protons here. 1, 2, 3, 4, 5 and 6. There should be 6 groups of peaks. You can see here, there are 6 groups of peaks. Now go by the multiplicity pattern. That's what I just now said. And here this CH3 is coupled to this CH2. That has to be a triplet. Okay, this could be 1, let us say. There are 2 CH triplets here. Which we'll see later. This one is a triplet. And this CH2 has to be a quartet because of the CH3. Where is the quartet here? This is the only quartet. And there is no other coupling possible because they are separated by several bonds. 1, 2, 3, 4 bonds away. Coupling is almost 0. So you will not see. So this has to be a quartet, this has to be a triplet. 2 groups are identified. Then if you come here, this CH3 has to be a triplet because of this CH2. So another triplet is there. And then this CH2 is quartet and then also become a triplet because of this. Like I said in the previous example, this is a very complex one. This is going to be like this. Whereas this one is going to be triplet of triplets like this. Whereas this is the only isolated CH2 group which is coupling only with this, not any of the other protons. So this is going to be a CH triplet. Very easily you can make the analysis. Now the question is which triplet is which, whether this or this. What you have to see, look at the separation here, coupling. Which one matches with this one, whether this or this. You can identify because this is quartet is coming because of this. Then you know this coupling has to match. It should be identical. From that you can identify whether this CH3 is this one or this one. So very easily you can do that. So this is how analysis can be done. Now of course, this is another very simple molecule. Look at the proton here, CH3. There is no other coupling for this proton, CH3 proton. All the 3 protons are equivalent and there is all other remaining protons are far away situated. So what is the pattern you expect for this? A singlet. That's what you get. That's simple. I can assign this as CH3 group. Next, look at this one. This is, I call it as 3 because this is CH3 group which is coming high field. At the same time, this is going to be a doublet because of this proton and another doublet because of this proton. It is going to be a doublet of doublet with 2 couplings between these 2 protons. So I can safely say this is proton 3. Very good. Then what is the other thing which I have to understand? Only remaining 2 protons, So which are the remaining 2 protons? I will say this is proton 2. This is proton. This is because this has 1 3-bond coupling with trans and also CH3 coupling, 4-bond coupling. This is for proton 4. Now this is proton 2. So in the case of proton 2, this is coupled to proton 4 and it is going to be a doublet, and each line of the doublet is going to be a quartet because of CH3. See 1, 2, 3, 1, 3, 3, 1, 1 quartet, 1, 3, 3, 1, another quartet. 2 quartets are overlapped. So this has to be proton 2 and this has to be proton 4. Like this you can start making the assignments. So we can keep on talking a lot about these things. There is no end for it. I'll go into the spectrum where, okay, this is where you have to use the knowledge of cis and trans coupling. I'll take this example. This is where I told you, trans coupling in this, in the double bond ethylenic groups like this, I told you trans coupling is larger than cis coupling and cis is larger than geminal coupling. That idea can be utilized to analyze which proton is which here. For example, this CH3 is isolated, is a single peak, is a singlet, no coupling at all. That's clear. Now between these 3 protons, which is which? Very easily you can understand. Look at this CH proton. One CH proton has a trans coupling and a cis coupling. Which is that one? This CH3 proton has a trans coupling with this, is a large coupling, 14 hertz. CC trans coupling is 14 hertz, and also it has a cis coupling. Both are simultaneously present. Cis coupling is 6.6 hertz. So it is a large doublet, and each line of the doublet is going to split into a doublet of a doublet like this. So this has to be this proton. Using the knowledge of cis and trans coupling, I could assign this. Now the remaining two. What about this proton? This proton experiences a trans coupling with this and a geminal coupling with this. Geminal coupling is very small. Where is it? We can see. This is the only possibilities here. Large coupling and a small coupling of 1.5 hertz. So this has to be this proton. And what about this proton? This proton experiences the cis coupling here. At the same time, it experiences the geminal coupling with this. That is this. So very easily you can start analyzing everything. Okay. So now I'll go to a molecule where it need not be proton coupling. If you are observing proton spectrum, you can get heteronuclear couplings also. For example, in this proton spectrum of this molecule, there are two proton groups, CH2 and CH3. But each of them has a coupling with phosphorus, which is spin-off nuclei, and fluorine, which is spin-off nuclei. Both of them are 100% abundance. So it is quite likely there is a coupling of CH3 to CH2, phosphorus and fluorine. Similarly, this can couple with this and this. We will see the pattern now. Now, as common sense tells me, as I have been telling you, in the high field region, methyl will come. This methyl proton is here. This has to be a triplet here because of this first. It's a triplet. Very clear. At the same time, it is also another triplet of a triplet because of this fluorine coupling. Two equivalent fluorines. Very clear. What about phosphorus coupling? It is not there. That coupling is 0. That is why CH3 proton gives triplet of a triplet. It has a one triplet because of this CH3 proton, another triplet because of two fluorines. So we are going to get triplet of triplets. Whereas we come to this group, this CH2 group, this CH2 becomes a quartet because of CH3. I will erase that and you will see that now. The CH2 becomes a quartet because of this CH3. That's correct. So now, because of this, it is a quartet. At the same time, you see, it is also has a coupling with phosphorus and also coupling with fluorine. But if in the coupling information given here, you see, proton phosphorus coupling is quite large. So it is going to be first a large doublet, 8 hertz, because of phosphorus and proton coupling. Second is proton-proton coupling, this the coupling. So then it will become a triplet. Further, each line of this triplet of triplet become triplet because of fluorine. Each of them will be triplet like this. So it will get a complex pattern like this. This is pattern. This is why I gave a lot of examples in the multiplicity pattern. This is a doublet of a quartet of a triplet. So in this example, I deliberately took, you have proton coupling and also coupling with two other heteronuclei. You may not be observing, what about PF coupling then? Remember I explained to you, these are passive nuclei. Passive coupling is not going to be seen, we are observing proton. So this passive coupling between phosphorus and fluorine is not seen here. So you will get only proton coupling, active coupling with passive spins, proton to phosphorus, proton to fluorine, proton to proton you see, but not other couplings. So this is a very useful information. You can start analyzing this. So I don't think this I will explain. Now I will go to the carbon 13 NMR. Carbon 13 is another extensively utilized NMR nuclei. Most of the time in organic chemistry or biology, people use carbon 13, nitrogen 15 and proton and phosphorus. These are extensively studied nuclei. Let us see how does the carbon 13 NMR looks. First of all, remember there are 3 isotopes for carbon, 12, 13 and 14. 14 you ignore, it is radioactive, we don't see it. The good thing in the nature is carbon 12 is 99% abundant, almost 99%. But we will not see that. You know why? I explained to you carbon 12 has spin equal to 0. So it magnetic moment is 0, it cannot give NMR. So it is NMR inactive. They are NMR silent nuclei. Now on the other hand, carbon 13 is 1% abundant. that is NMR active. Interestingly, it is the spin-off nuclei. Very easy to study. Very easy to understand the behavior of spin-off nuclei. So another salient point is what are the factors that affect chemical shift of protons, which we discussed. Same thing applicable for carbon 13 also. Here also use TMS as the reference like in proton. And only thing is gamma of proton is 1/4 that of the proton, gamma of carbon. As a consequence, the resonating frequency is 4 times less than that of proton. That's what we discussed last time. If I have a spectrometer of 400 megahertz, that means proton resonates at 400 megahertz, carbon 13 comes at 100 megahertz. That's what it is. Okay, that's what. So, but chemical shift range, if you look at it, chemical shift range of carbon 13 is also 0 to 300 ppm. It is not 0 to 10 ppm like proton. This chemical shift range is much larger here. So take TMS as the reference, put it at 0 ppm, and you will see peaks anywhere from 0 to 300. Of course, in special cases, you can go beyond 300 also. I am just taking, by and large, in most of the cases, it is between 0 to 300 ppm. So this is the chemical shift range of carbon 13. Now another thing is, carbon 13 we always obtain by decoupling proton. What is a decoupling? I have not discussed, but for that please go back to my previous course. Broadband decoupling means simultaneously we break the coupling of all carbons with all other protons. That means in a given molecule there may be n number of carbons. Each carbon may be coupled to n number of protons, different protons which are chemically inequivalent, and some equivalent groups which are present elsewhere in the molecule. But that will give rise to complexity. One carbon, if it is with a CH3 carbon, it will become quartet. If it is coupled to another CH2 proton, then it will become quartet of triplet. All those complexity will come. And already carbon 13 is less abundant, 1%. Sensitivity is 4 times low gamma compared to proton. So it is very difficult. Why should we have multiplicity pattern, which complicates the situation? So always carbon 13 NMR is recorded by doing what is called the broadband decoupling, where all protons coupled to all the carbons are simultaneously removed. How we do that is a different question that we have discussed in the previous course. Then what will happen? There is no coupling of carbon with proton at all. What does it mean? If I have a CH3CH2OH ethyl alcohol, I look for carbon 13. I break the coupling of carbon with protons. So that means there is no coupling between carbon and proton. For CH3 I get one peak, for CH2 I get one peak. That's all. It means for each chemically individual carbons we get only one peak. So if there are n number of peaks, you can simply say there are n carbons present in the molecule. That is the simple thing. Salient points of carbon 13 number is, it is done, it is recorded with broadband decoupling, remove all the proton carbon couplings. As a consequence, if there are n number of carbons in the spectrum, there are n number of peaks, there are n number of carbons. Very easy to identify. Okay. But then you may ask me a question like heteronuclei. In the previous example, we saw proton, carbon, fluorine, phosphorus was there. You remove the coupling between carbon and proton, broadband decoupling, but not with other nuclei. You can do special experiment by removing everything. That's a different question. But if you are broadband decoupling proton with carbons, if the fluorine is present or phosphorus is present, they are still coupled. Remember, that is we are not removing. So multiplicity still can be present. So we will take some examples. As I said, Zeeman interaction, energy separation is larger for proton because it is 4 times more gamma than that of carbon. As a consequence, energy separation is less, 4 times less here compared to proton. So sensitivity is much less here. So in an 800 megahertz spectrometer, I get proton at 800 megahertz, carbon 13 comes approximately at 200 megahertz. So more details, carbon 13 which has sensitivity in principle 5670 times smaller. In the previous class we saw that taking into account gamma, it goes to by cube of gamma, and taking into account natural abundance, we showed that it is gamma cube approximately 64 we took, and then 1.1% in the abundance if you consider, it is 64 into 100, 6400 we said approximately. So if you precisely calculate, this is the number of times it is less sensitive compared to proton. But signal to noise ratio, when I acquire the signal, it goes by square of the number. If I acquire 4 scans, then signal to noise ratio will be root of 4. It is going to be 2. So I have to multiply this by this to get good signal to noise ratio. So all these things tells me carbon 13 NMR is more time consuming than proton NMR. It's very, very time consuming, very less sensitive, very difficult to detect. Now I'll give you some very salient points and interesting features about carbon 13 NMR. Let us consider an example of a molecule like CHCl3. We'll talk about isotopomers of the molecules. I consider 100 molecules are there in my sample tube, an ensemble of 100 molecules. According to me, the abundance of carbon 13 is only 1%, abundance of carbon 12 is 99%. So in an ensemble of 100 molecules, we have 99 molecules which are carbon 12 and only one molecule has carbon 13. But this is NMR inactive and this is NMR active. So you will see only one molecule with carbon 13 in its carbon state. All other things are carbon 12, which doesn't give NMR at all. So now what happens if I have a molecule with 2 carbons present? Let us consider what will happen. I consider a situation, some hypothetical molecule. 2 carbons are present. I have not completed the structure of the molecules. Don't worry. Now there is a possibility both carbon can be in carbon 12. That is 98.9% present. So if you take the factor multiplication, this 97.8% of the molecules are this one. So that means majority of the molecules what you are observing are NMR inactive. Whereas consider the situation, one of the carbon is carbon 13, other is carbon 12. That's also possible. But this is only 1.1% abundant because this is carbon 12 is inactive. Think of another possibility. This is carbon 13, this is carbon 12. Again it is 1%. This is NMR active. So there are 2 molecules with 1% NMR activity and then 99% and 98% almost with 2 molecules with 2 carbons in carbon 12 state which are NMR inactive. They are NMR silent nuclei. So what is the possibility of 2 carbons simultaneously present as carbon 13? That's a very interesting question. Can there not be 2 carbons simultaneously in carbon 13? Of course there is a possibility. But then remember 1% of this and 1.1% of this, 1 in 100 will be in this position, 1 in 100 will be in this position. The joint probability of both the carbons in carbon 13 state is 1 in 10,000. So if you take 1.1% as the abundance factor, it turns out to be 0.000121%. That means in 10,000 molecules, you will see one molecule which is NMR active, where both the carbons are in carbon 13 state. So probability is 1 in 10,000 is extremely difficult to detect at all, such molecule. Okay, now take the other example, three molecules. What is the probability all the 3 are in carbon 13 state? You can immediately understand 1 over 100 into 1 over 100 into 1 over 100. So what is the probability? It is 0.4501331. That is 1 in a million. If you have million molecules in your sample, only one molecule there is a probability where all the carbons are in carbon 13 state. Now extend the logic. I don't have to keep on doing the arithmetic. Go to a simple molecule like this, very big molecule with 6 carbons are present. Hypothetical molecule, there are different substitutions, don't worry, there is no symmetry in this molecule. All carbons are inequivalent. There are 6 carbons. What is the probability of seeing all the 6 carbons in carbon 13 state? It is such a small number. 1 in a quadrillion, 1 in 10 to the power of 12. So many number of molecules. If there are present millions and millions of molecules, millions, 10 to the power of 12 molecules, if you can think of it, there may be one possibility, only one molecule has all the carbons in carbon 13 state. So now the question I am going to pose is, How can we see all the carbon peaks in a molecule containing large number of carbons? True, we have seen carbon 13 spectrum. Take a molecule, put in a magnet and record the NMR spectrum. You see carbon 13 spectrum with 10 or 20 lines or 30, 50 lines present. How can we see when the probability like this is so low? Even for 6 carbon, I said it is only in a quadrillion. If there are large number of carbons, 10 or 20 or 30 carbons present in your molecules, how can you see the carbon 13 spectrum? This is a difficult question one need to answer. So next, before going further to understand that, let us see how does the protons attached to carbon 13 influence the spectrum. If proton is attached to carbon, Ca3 proton is there are 3 equivalent protons. I told you it has to be a quartet because there are 3 equivalent, 3 protons coupled to this, 1:3:3:1 intensity. If there are 2 equivalent protons coupled, it's a triplet. If it's only 1 proton coupled, it's a doublet. If there is no proton coupled, each carbon is going to be a singlet. So imagine if all the different functional groups are present in a molecule like this, you will get a quartet, singlet, doublet, triplet, very complex spectrum you are going to get. Now my question is, how we got all the carbon line peaks in a straightforward way, in spite of the fact the abundance or the probability of seeing all the carbons in the carbon 13 state is 1 in 100. If that is the situation, how do we see carbon 13 spectrum? We will understand by taking a simple molecule. Ethyl alcohol, 2 carbons are present here. We already discussed what are the possibilities of carbon 13 present here. We said this is carbon 13, this is carbon 12, 97 point, both are carbon 12, 97.8% NMR silent nuclei. Carbon 13, this is carbon 12, 1.1% NMR active. This is carbon 13, this is carbon 12, 1.1% NMR active. And now probability of finding both in carbon 13 state is 0.00012 to 1%, which is NMR active. So the signal from this isotopomer I am not detecting at all. Remember, this signal is not coming. This molecule I can ignore. This isotopomer I can ignore. Now I have only 2 isotopomers I have to deal with. Which are they? I can ignore this one. It doesn't give NMR. Only this gives 1% active NMR active. This is 1% NMR active. Whereas this I will ignore because abundance is too small. So I have to consider only 2 isotopomers. Let us look at the spectrum of 2 isotopomers. How does it come? First consider this molecule, where this is carbon 13, this is carbon 12, this carbon. What is the type of spectrum you get? I just now showed you, if there is Ca3 group present, you will get a quartet. Perfect. You will get only quartet for the spectrum. This carbon will not give signal because carbon 12 state NMR inactive. Now I will consider other molecule. This is carbon 13, this is carbon 12. What is the pattern you get for this? I just now showed you for CH2 group, carbon has to be a triplet because it is attached to 2 equivalent protons. Now in reality, in a ensemble of molecules that are present in the NMR tube, both these molecules are simultaneously present. The spectrum is a superposition of both the spectra. So you are going to get a quartet and you are going to get a triplet. In a spectrum, when you take the spectrum of this molecule, in reality, you will get a spectrum like this. This is a realistic spectrum. You get a quartet and a triplet. You are not separating the molecule like this, one for CH3, one for CH2 like this. In a given tube, both are present, so you get a superposition of both the spectra. So what about C13, C13 coupling? As I told you, we don't see it, we can ignore. But remember, coupling is not zero. Coupling exists, not zero. But you don't detect it because of very low probability of seeing such type of molecules. So what now the question is, we can ask a question. We discussed carbon 13 proton like this, okay. This is a quartet, this is a triplet, everything. But what about this proton coupled to this carbon? Can these 2 protons couple to this carbon? Can these 3 protons couple to this carbon? Why not? It should be possible, right? It is possible. So in principle, what you are going to see is, you will see long range proton carbon couplings also. See, you will see everything actually. So CH3 carbons will be a triplet. I'm sorry, CH3 carbons will be a triplet because of the CH2. CH3 carbon is going to be a triplet because of, first of all, it is a quartet because of 3 protons, and it will be further split into triplet because of CH2 protons. Very important. This is the additional triplet coming because of CH2 protons. See, it is going to be a quartet, and each quartet is going to be a triplet because of coupling with CH2 protons. Very easy. So this is, now what about this one? This is going to be a triplet because of 2 protons, and each line of the triplet is a quartet because of long range coupling to CH3 protons. So what you are going to get, CH2 carbons will be a quartet because of coupling with CH2 protons. So first it is going to be a triplet because of CH2 protons, and it is going to be further split into quartet because of CH3 protons. So the pattern taking into account only JCH coupling, 1 bond proton carbon coupling, if you consider for ethyl alcohol, CH3 will be a quartet, CH2 will be a triplet. Now if you take proton and carbon, it is CH coupling, 1 bond CH and 2 bond CH couplings. If you consider carbon remote carbon proton couplings also, then you get triplet of quartets and then quartet of triplets. This is the real spectrum what you should see for ethyl alcohol if you take it and take the spectrum. So this is a realistic molecule. You can see a molecule like this, a CH2 is a large triplet, and each line of the triplet is a quartet because of CH3, and this CH2, this CH3 is a quartet because of 3 protons, and each line of the quartet is a triplet here because of this CH2. And similarly in the aromatic protons, you can see doublet and quartets, everything will come depending on long range couplings. Very easy to understand. So remember this statement. It's a very, very important statement. For a molecule with n chemically non-equivalent protons and n chemically non-equivalent carbons present, a molecule, consider a big molecule, n chemically non-equivalent protons are there. So n groups of proton signals are there. N chemical non-equivalent carbons are there. There are n carbon peaks which are coupled to protons. So in reality, the proton spectrum is obtained from a single molecule. All peaks coming from one molecule because they are 100% abundant. Whereas carbon 13 spectrum is the superposition of the spectra from n isotopomers, and each isotopomer containing at least one carbon in different carbon 13 state. That is the important point. You remember, carbon 13 spectrum is not from a single molecule. It is from n number of molecules. There are n carbons in which each spectrum corresponds to one molecule where one carbon is in carbon 13 state. That is the important point. So now question is, generally you get a carbon 13 spectrum like this. How do we simplify this? If you get like this, with all couplings of long range proton carbon, 1 bond proton carbon couplings like this, then it is very, very complex. This is as complex as a proton spectrum to analyze. But I said in the beginning, carbon 13 we record with a broadband decoupling, where all coupling to all carbon to proton are simultaneously removed. If you do that, then broadband decoupling, you get only one peak for each chemically inequivalent carbon. That is what we do. In carbon 13, is always recorded, or usually I would say recorded, the broadband decoupling. So when you do the broadband decoupling in a simple way, this is what we discussed in the previous course. You have a carbon 13, you apply the decoupling power continuously, in which when you are observing, you apply a radio frequency pulse simultaneously with the proton channel continuously to saturate these protons. This carbon 13 will not, you are detecting, it will not see this proton in either alpha state or beta state. As a consequence, the coupling between carbon and proton is broken. And this is how the spectrum gets simplified. Look at this, the quartet, a CH3 group. Now it becomes broadband decoupling makes it a singlet. This is a triplet, broadband decoupling makes it a singlet. Each doublet like this for aromatic protons will become singlets like this. Very easy to understand. So in a complex molecule which I showed you, a cholesterol molecule which is so complex, how do you simplify now? Do the broadband decoupling. What is the advantage? Each peak here corresponds to one carbon. Measure the number of peaks present here, except this, which is the solvent chloroform. Then you can find out that many number of carbons are present in this molecule, if there are no other heteronuclei which are coupled to it. So in this case, there is no other heteronuclei, fluorine, phosphorus, etc., which are coupled. So as a consequence, just count the number of peaks, 1, 2, 3, like that. That many number of carbons are present in the molecule. That is the easiest way to understand. Okay. So what I am going to do is, I think time is up. I will stop here. We will continue the analysis of remaining spectra in the next class. But what basically I want to tell you is this one. You would have understood by now. We understood lots of NMR interaction parameters. Now in this class we understood how to analyze the spectrum. Different proton spectra based on the multiplicity, based on the chemical shifts where they come, different functional groups where they resonate, depending upon the neighboring groups which are adjacent to that, how the multiplicity arises, we try to interpret the spectrum. Couple of examples we took. In the carbon 13 we know carbon 13 abundance is only 1%, carbon 13 is NMR active, carbon 12 is NMR silent. As a consequence, we also understood if there are n number of carbons simultaneously present in the molecule, there is a probability that all carbons can be in carbon 13 state, but it is extremely small. If there is a large number of carbons, it is almost impossible to see all carbons in carbon 13 state. But then we can think of isotopomers. Each carbon in carbon 13 state can be present, where remaining can be carbon 12. So you can consider the number of isotopomers. So we understood the carbon 13 spectrum is the one which is a superposition of the spectrum for each individual molecule, where each in the individual molecule at least one carbon is in carbon 13 state. And then generally I said carbon 13 spectrum is a superposition of the spectra of all the carbon 13 isotopomers. You can get long range couplings in addition to one bond coupling, but that we can remove by decoupling. That's what also IV said. So whereas in the proton spectrum, it is from a single molecule, carbon 13 is from superposition of the spectra. And we try to understand some of the spectra like this. We'll stop here, come back and continue the analysis further. With that, we'll go to the different topic later. Thank you.